Have you, like me, been admiring the beauty of our planets through the pictures NASA blesses us with almost every day? It has been 6 years since the Juno spacecraft began its orbit around Jupiter, during which time it has been collecting incredible images and data from the massive planet. Juno is a game changer for our knowledge about the outer part of the solar system, and it is getting closer to the end. Over the past months, Juno's findings challenged our previously held beliefs about Jupiter's atmosphere, seeing unusual lightning strikes above its clouds. Who would have thought? What could have been the cause of this lightning? And what else did Juno see during its journey? Keep watching to find out. In 2021, Juno began an extended mission that included flybys of Jupiter's icy inner moons Ganymede, Europa, and Io. It had been over 20 years since Galileo visited these moons, and NASA is eager to learn what might be occurring underneath their frozen surfaces. Excitingly, preliminary results suggested that a lot is transpiring. Furthermore, we are able to capture exquisite images of these frosty moons due to the powerful cameras aboard Juno, such as JunoCam and its Stellar Reference Unit navigation camera. We are truly grateful for the technology that enables us to obtain such incredible images. With the imminent end of its long mission coming soon in September 2025, let's take a look at some of the magnificent images JunoCam and its Stellar Reference Unit navigation camera have caught of the icy moons. Revisiting Juno's extended mission will explore some of its exciting discoveries that are reshaping our knowledge of the Jovian system. Let's first remember how this mission started. In August of 2011, Juno set off on its mission from Cape Canaveral, Florida. After an incredible journey of 2.8 billion kilometers spanning 5 years, it finally entered Jupiter's orbit on July 5, 2016. After accomplishing its basic goals, NASA added 42 more orbits called Precautions to Juno's mission, with the planned deorbiting and burning up of the probe in Jupiter's atmosphere by 2025 to prevent any potential contamination on the moons. In order to comply with NASA's planetary protection guidelines, extra caution is being taken with Juno's mission. This precaution is especially important since scientists have speculated whether life exists on the inner moons of Jupiter. NASA is making sure not to interfere with any potential discoveries that could be made about these moons. On June 7, 2021, Juno's close flyby of Ganymede used a gravity assist to decrease its orbital period from 53 days to 43 days. In contrast, a distant flyby of Ganymede in 2019 saw Juno reach a distance of 97,000 kilometers, but the probe was brought to within just 1,000 kilometers of the moon's surface during the 2021 encounter. Ganymede. This stunning photograph taken by JunoCam offers an almost complete look at Ganymede's surface at a resolution of 1 kilometer per pixel. Its texture is incredible. You can almost feel it when looking at the image. There are various distinctions that appear, with dark areas representing older, heavily cratered terrain and lighter regions reflecting younger and less impacted landforms. An array of craters, light and dark spots, and long striations also decorate the icy surface. Scientists hypothesize that the long striations you see on the surface of Ganymede are evidence of tectonic movements created by the heat from the moon's iron-nickel core. Previous data suggests that it contains an immense salty subsurface ocean beneath its icy outer layer, which could potentially be home to life. This is an area of research that is currently being examined. This image was taken on June 7th during a flyby and shows an incredibly detailed view of Ganymede's Tros crater, representing the dark side of the moon. It appears to be very bright because it is covered in ice. The camera used to capture this photograph was the Stellar Reference Unit navigation camera, designed to use starlight to guide Juno. With a resolution of 600 to 900 meters per pixel, we can clearly see the moon's striations and craters, some of which are stacked atop each other. We have seen a lot of photos of Ganymede, many of which I've previously seen, and the level of detail in the shots taken by Juno in low light is truly remarkable. It is certainly intriguing to note that one of the most remarkable discoveries from the mission emerged from Hubble. Indeed, the famed Hubble Space Telescope was able to provide certain insights that were extraordinary. Let's dive into it. NASA asked Hubble for a little favor. They asked it to observe Ganymede's ultraviolet signals in order to assist Juno's research of the Jovian moons. Ganymede, although having a very thin atmosphere, was speculated to contain oxygen, yet the ultraviolet emissions revealed something different. To everyone's surprise, rather than oxygen, the atmosphere contained a large number of water vapor. This finding has caused us to drastically revamp our model of Ganymede's atmosphere, indicating that water vapor may be present in the atmospheres of icy celestial bodies around the solar system. Europa. After completing its visit to Ganymede, Juno was given a gravity assist on September 29, 2022, during its flyby of Europa, which allowed it to reduce its orbit to 38 days. We are pleased to present to you an image captured from the flyby, taken from a distance of 351 kilometers. This image shows a portion of Europa just north of the equator. It's absolutely marvelous. The view we have on the day-night boundary of the Terminator, as the deep shadows enhance the ridges, troughs, and craters of the moon's surface. It almost gives it a three-dimensional appearance. Researchers believe that Europa and Ganymede likely contain large oceans underneath their icy surfaces. However, recent discoveries indicate that more complex events may be occurring than originally thought. This image was captured by Juno's Stellar Reference Unit camera and is a close-up of a section of Europa's surface. It was taken from a distance of 412 kilometers in the night hours on the moon. This image, captured by Juno at a resolution of 256 meters per pixel, is the highest resolution picture of Europa. Upon looking at it, you may wonder what it is you are seeing. The fractured region of Europa's surface is made up of grooves and ridges of ice, and that dark spot near the middle could provide valuable information about the geological complexity of the area. It is thought that the dark area is a sign of a volcanic eruption below the thick layer of ice, which is speculated to be around 10 kilometers thick. The pressure required to penetrate such an amount of ice is immense. A new paper recently released by the American Astronomical Society presents a revolutionary theory with an alternative explanation. The authors of the paper suggest that Europa's cryovolcanism implies the presence of brine reservoirs held within the planet's icy crust. It is possible that there may be high salt content brine lakes located far above the moon's subsurface ocean, which can swell and expand the ice around them like a balloon and burst out periodically. We may have to wait until 2030 for the European Space Agency's Clipper mission to reach Europa in order to prove this mind-blowing theory. Although that is 8 years away, it's never too early to start counting down the days, as you know, time flies. Before we move on with the exploration, stay tuned afterwards if you'd like to watch our earlier release on Journey Without Return in the hellish atmosphere of Jupiter. Jupiter. The Voyager mission's 1979 visit to Jupiter uncovered a mysterious phenomenon, bright flashes in the planet's atmosphere. Scientists initially thought it could be lightning, which indicated the presence of water in its three forms: solid, liquid, and gas. With Juno's visits to Ganymede and Europa, the decades-long mystery was finally solved. Given what we know of Jupiter's atmosphere, this would put the storms at least 45 kilometers below the visible cloud tops. However, Juno disproved this theory, and the truth is stranger than we imagined. Juno's groundbreaking findings completely overturned our prior understanding of Jupiter's atmosphere. The spacecraft's Stellar Reference Unit camera captured something unusual: nighttime flashes of light at an altitude much greater than expected. Scientists determined that these storms were composed of ammonia water clouds, a phenomenon that does not occur on Earth due to the extreme cold temperatures at this altitude, reaching below minus 88 degrees Celsius, a staggering 45 kilometers above the visible cloud tops. The ammonia acts as an antifreeze, combining with 2 parts water and 1 part ammonia to form a solution that stays liquid, even in the extreme cold of these intense and unpredictable thunderstorms. Powerful lightning strikes are accompanied by hail made of water ammonia slush, which scientists refer to as mush balls, an unusual type of precipitation. So let's recap. What has Juno discovered so far, and what are its next targets? Juno has uncovered unexpected levels of chaos and complexity at Jupiter during its time in orbit. This includes the discovery of Earth-sized storms at both of Jupiter's poles and a cluster of cyclones and anticyclones at the North Pole. NASA has been amazed at what Juno has revealed regarding the gas giant. Research suggests that Jupiter's core may not be as solid and compact as previously believed, but rather fuzzier and larger in size. This hypothesis has been furthered by data gathering by the Juno spacecraft, which, despite being unable to observe the core directly, has provided evidence for the theory. By studying Jupiter's atmosphere with Juno, scientists have discovered a new form of lightning. This type of lightning, called shallow lightning, does not occur in Earth's atmosphere as it is not composed of water clouds. Instead, it is caused by the collision of ice crystals and ammonia in colder, higher regions of Jupiter. We're all eagerly anticipating Juno's arrival at Io in 2023. Past performance indicates it will be yet another successful mission that reveals more about this intriguing moon. Ganymede and Europa have already provided us with exciting discoveries, so the possibilities for Io are endless. Since beginning the Juno mission, we have been continually amazed by the strange, unexpected discoveries made about Jupiter. We are eagerly looking forward to what will be uncovered when Juno reaches Io in 2023. Jupiter is the largest and most massive planet in the entire solar system. It is so large, 140,000 kilometers in diameter, that if we put together all the other planets, including Saturn, we would be able to equal only half of its mass. It is difficult to describe in words the fascination that this cosmic giant has exerted over the centuries on entire generations of astronomers, enthusiasts, and simply curious. On Jupiter, everything is out of scale, starting from its best-known feature, the red giant spot, a huge cyclone that rages in the atmosphere of the planet for at least 350 years. Like Saturn, Uranus, and Neptune, Jupiter is mostly composed of gas, especially hydrogen and helium, and therefore has no defined surface on which to land. A hypothetical descent into its atmosphere would look very much like a very long dive into the depths of the ocean. Although we do not know all the secrets of Jupiter yet, we know just enough to imagine the wonderful and terrible spectacle that a hypothetical astronaut would see if he tried to venture into its turbulent atmosphere. Alien colors, clouds as big as mountains, immense columns of gas in continuous movement, lightning so powerful that an entire ocean evaporates in the space of an instant. On Jupiter, every atmospheric phenomenon is taken to the extreme to characterize one of the most hostile environments of the solar system, an environment that few remember we began to explore a quarter of a century ago. So much time has in fact passed since the day the Galileo probe arrived on Jupiter after a 6-year journey. Among the main objectives of that mission, in addition to the study of the Medicean satellites and the Jovian magnetic field, there was also the analysis of the atmosphere, for which was designed a small probe called atmospheric that would measure pressure, temperature, and chemical composition. Galileo released the atmospheric probe 5 months before meeting Jupiter, in July 1995 and on December 7, 1995. The two ships reached the gas giant together. The mother probe entered into an orbit around the planet, while the little one penetrated its atmosphere at a speed of 48 kilometers per second, after which, in little more than 2 minutes, it was slowed down to subsonic speed by the density of the air. The descent lasted a total of 58 minutes, and the connection was interrupted when the probe arrived at 150 kilometers of depth, reached conditions of temperature and pressure so high that it dissolved in the atmosphere of the planet. The data collected along the way proved to be of fundamental importance to understand the dynamics and chemical composition of the upper layers of the Jovian atmosphere, but did not provide any clue as to what lies deeper. However, nothing prevents us from putting together what little we know with a bit of imagination and fantasize about what we might see as we descend towards the core. En route to Jupiter. We are 500,000 kilometers away from Jupiter, aboard our ship, and the approach phase is much longer than expected. We are navigating at the maximum speed allowed by our propulsion system, yet it seems that the planet is not approaching 1 meter. The outermost layers of its atmosphere begin to occupy the entire field of view only after several hours of travel, when we are still 200,000 kilometers away from the apparent surface of the planet, that is, from the top of its highest clouds. Now the entire disk of the planet extends into the sky for about 40 degrees of apparent diameter. Finally, we see in detail the dense clouds of ammonia and hydrogen that rotate in parallel around the equator, forming the characteristic white, red, and orange bands. Jupiter, as well as the Sun and Saturn, is in fact subject to a differential rotation phenomenon. Because of its high speed of rotation, 9.9 hours, the gases that make up the upper layers of the atmosphere, mainly hydrogen, helium, and ammonia, move at different speeds depending on their position with respect to the equator, creating the characteristic horizontal bands of different color. Usually the red ones, called zones, correspond to atmospheric depressions caused by descending cold air, while the lighter ones, the bands, are cloudy reliefs formed by rising hot air. The Great Red Spot, so clean and geometric if seen from a distance, slowly begins to transform, so that after a few hours we find it hard to distinguish the contours. The enormous vortex, which from space seemed to us a single structure, now appears as a chaotic set of smaller vortexes, whose circumvolutions reveal new and unexpected details about the extreme turbulence of the atmosphere. The mighty columns of gas emerging from the deepest layers of the planet make Jupiter resemble a huge pot full of bubbling water. Arrived at 100,000 kilometers from the surface, the electromagnetic bombardment caused by the Jovian magnetosphere is so intense that we are forced to activate the special protections of our ship. If we did not, we would die of radiation poisoning within minutes. Jupiter is in fact like a giant dynamo. Because of its fast rotation period, the speed with which the metallic hydrogen slides on the inner core of the planet generates strong electric currents that give rise to a magnetosphere 20,000 times more powerful than the Earth. The magnetosphere then traps solar emissions in huge bands of radiation, generating a radioactive environment that is a deadly risk both for probes, whose instrumentation must be adequately shielded, and for astronauts. 0 kilometers. The descent begins. Continuing our journey, we finally reach the edge of the troposphere, the zero limit from which we begin to measure the descent, as we would do with the depths of an oceanic trench. The long descent to the innermost layers of the gas giant begins here. We disengage from the spacecraft, protected by our magical spacesuit, and let gravity drag us towards the core. Because of its enormous mass, at this height Jupiter generates a gravitational acceleration 2.6 times higher than the Earth. So if we want to avoid burning like a meteor, we have to open a parachute to slow the fall. We do it, and in a few minutes our speed goes from 3,200 to 360 kilometers per hour, with a deceleration that allows us to avoid any risk of supersonic compression or overheating due to friction. Minus 10 kilometers. Along the mists of the Great Red Spot. Looking around, we notice an unusual landscape. The colors vary from bright red to brown, and there is a thick layer of mist that prevents us from pushing our gaze further than a few hundred meters. But if we could do it, we would see a spectacle without equal. The clouds that surround us, up to 45 kilometers high, and composed mainly of hydrocarbons, hydrogen, methane, and ammonia crystals, would look like huge mountains. We would immediately notice that ammonia covers the upper surface of the clouds like an oil film on water, adding a hue of white to the dominant red color. Pushing our eyes even further in the direction of the Great Red Spot, we would see a huge column of turbulent gas soaring over the surrounding clouds, almost as if it were floating above the troposphere. Minus 50 kilometers. lightning, and turbulence. At the height at which we are now, about minus 50 kilometers from the beginning of the troposphere, the conditions of pressure and temperature are similar to those detectable on the surface of the Earth, but the winds raging around us are dragging us at speeds of over 560 kilometers per hour, and the intensity of radiation generated by the Jovian magnetic field could still kill us in a few minutes in the absence of protection. The noise generated by the turbulence is deafening, because here the speed of sound is 4 times higher than we are used to. The sky is continuously crossed by violent lightning tens of kilometers long, thousands of times more powerful than those generated on Earth. The lightning is mainly caused by rains of water, sulfuric acid, and ammonia, which, due to the gravitational attraction of Jupiter, fall at a speed 3 times faster than the Earth's rains, creating a huge difference in potential. Minus 100 kilometers. Goodbye to the light. After another 5 minutes of descent, the atmospheric pressure rises to 2 bar, and we begin to cross a new layer of clouds, this time composed of ammonium sulfite and ammonium hydrosulfide. The conditions of the environment around us are quite extreme, but at this moment we do not need any additional protection other than good radiation shielding. Although the weight of the air above us starts to grow following an exponential curve, the relatively low fall rate allows the cavities of our body to equalize their internal pressure without generating undesirable effects. Another 10 minutes pass and the pressure reaches 4 bar, a value corresponding to what we would experience on Earth by diving into water at a depth of 30 meters, while the temperature drops to minus 40 degrees. We begin to encounter the first clouds of frozen water, and in the meantime, the ambient brightness continues to decrease. The speed of the winds rises to 720 kilometers per hour, but we barely notice it, because the level of turbulence in the atmosphere gradually decreases. Another 15 minutes of fall and the pressure rises to 10 bar. At this point, in order to avoid harmful effects on the body, we have to modify the air mixture supplied by the suit's respirator. If we do not do it, in a few minutes we would encounter an oxygen poisoning or a nitrogen narcosis, because under pressure the 2 gases become toxic. Let's take a last look above us, just in time to see the weak disk of the sun disappearing in the orange fog. Another 25 minutes pass and the situation begins to get complicated. The special protective suit with which we are equipped must withstand a temperature above 100 degrees Celsius, continuously and constantly increasing, accompanied by enough atmospheric pressure to crumple a car. We find ourselves suddenly immersed in darkness, and we can no longer distinguish anything. The absence of light is due to the density and chemical composition of air. Around us now there are only nitrogen, helium, ammonium sulfide, and traces of water vapor compressed to the point of absorbing all the electromagnetic radiation coming from the sun. Our journey has turned into a slow fall into darkness. Minus 20,000 kilometers. Gases become liquid. We continue to slow down due to the increasing atmospheric density, while incandescent helium is raining around us. The gases compress more and more, starting to behave like liquids. If we had to leave our protective suit, we would be crushed and vaporized in a split second. Now we are no longer even able to determine where we are in relation to Jupiter's core, because the transition between gas and liquid is so gradual that we cannot realize the change in density. Below us, at an unspecified distance, we notice a faint luminescence caused by the energy radiating from the nucleus. Atmosphere is now almost completely formed by liquid hydrogen that boils at thousands of degrees centigrade. As on the surface of the sun, the pressure rises rapidly from 1,000 to 2 million bar, and the atmospheric density has exceeded the water density by a while, reaching even 1,000 kilograms per cubic centimeter. At this point, the fall stops, because our body, being less than the matter around it, once exhausted the kinetic energy of the fall, can no longer sink. If we want to continue, we need a push. So we turn on the propellers of the suit and start to descend slowly again. Minus 30,000 kilometers. An ocean of liquid metal, From here on and for several hours, the journey is particularly boring. Darkness and silence dominate, and the monotony is interrupted only by the imperceptible flashes that emanate from the deepest regions of the planet. Continuing on becomes more and more difficult. After a time that seems endless, however, something unexpected happens. The darkness is torn by a web of lightning that vaguely resembles a spider's web. This network of lightning branches out following a very particular geometry, which closely resembles the way electricity propagates in the water. We are sailing in a vast ocean of metallic liquid hydrogen. Under normal conditions of pressure and temperature, hydrogen is a gas, but if its density exceeds a certain critical point, it turns into something different, a substance that flows like a viscous liquid and conducts electricity like a metal. The lightning we saw in the troposphere are nothing compared to those that cross this boundless ocean. Where we are now, pressure and temperature have reached such high levels that they escape any attempt at understanding. Minus 60,000 kilometers, the core. No matter how hard we try, we can't go any further. Below us now is the core of Jupiter, an extremely dense and warm core with a mass between 12 and 45 times the Earth's one. Astronomers believe that it is mostly solid and contains most of the heaviest elements of the planet, such as ice, rock, iron, and other heavy components, with a considerable amount of hydrogen. To be able to walk on its surface, we should be able to survive pressures 4 million times higher than the Earth's surface, and temperatures of over 35,000 degrees, a bit too much even for our imagination.